of this session is Preference Elicitation as an Optimization Problem by Anna Sepliarskaia, Julia Kiseleva, Filip Radlinski, and Maarten Rijke. None of them is here today, but the paper will be presented by Davis Graus.
Yes, that's right. So I'll start with a bit of a disclaimer. This is neither my work nor my domain of expertise, and I received these final slides this morning, so that's why I have this device in front of me with a few speaker notes. So yeah, I'm a former student of Maarten Rijke, and that's how you end up here. So let's dive into the paper. So first of all, what are the authors trying to address in this paper? So the paper is about solving, for a part, the new user coldstart problem, which is the problem when you have a user that has not rated anything yet. You cannot make any recommendations for this user. So one of the common solutions is to generate a profile by asking users to rate a bunch of items. So the topic the authors in this paper address is asking which items and how many items do you want to elicit responses from. Right, so the main research question in this paper is how to optimally generate a preference questionnaire consisting of relative questions for new users that will help to solve the new user coldstart problem. Now, the authors propose a new elicitation method which generates a static list of a static preference questionnaire. And static questions are questions that are chosen independently of the user and the answers that the users give, so it's the same for all users. The questionnaire poses relative preference questions which distinguish themselves from absolute questions, which I'll get into in the next slide. The method chooses a minimal and diverse set of questions and uses a theoretical reduction to an optimization task, which is detailed in the paper. We won't be going into it in these slides. Right, so the relative versus absolute part. So this is an example of a relative preference question. You have two titles, and you ask the user which one of these titles do they prefer, or whether they prefer them equally. Now, why would you go for relative questions instead of absolute questions? One is that explicit ratings suffer from the calibration issue, which means that for different users, the same type of rating may mean very different things. And users may change their opinion. For example, after having seen a certain item, then the next item may be rated lower. And finally, relative questions are faster to answer and are easier. So those are the motivations for looking at relative preference questions. Then on to the method. So now we understand a bit of the context and background. How to solve this. Right, so first of all, we start with an n times m-sized rating matrix, which should not be too unfamiliar for most of you in the audience, where you have a matrix of the size of the number of users and the number of items. And where each element in this matrix describes the feedback of a user on a particular item. Another important aspect of this work is the use of latent factor models. So the authors assume they have a latent factor model that's already trained, and that each rating complains with the noisy model shown in this slide. So I believe that's also quite familiar. So the idea is you have a global bias, you have a latent vector for an item, you have a bias for an item which corresponds to its popularity, roughly corresponds to its popularity. You have the same for the user, so a latent vector, and a bias, and the bias in the user case refers to the rating that the user predominantly provides, and you have some random noise. Okay, so that's the starting assumptions. Now the question is how this latent factor model can use the static preference questionnaire, I should think, as proposed by the authors. So it does so in two steps. So using a completed questionnaire with answered questions, the LFM gets a predicted latent vector of the user. That's the vector hat. While predicting the ground truth parameters. And the ground truth parameters in this case are the parameters of the trained latent vector model. Then the latent vector model uses this prediction to predict the relative preferences for a user over all pairs of items. And then we can measure the performance of this method in terms of the binary classification quality of item pairs. So the classifier estimates a user preference of an item, and you can measure the quality of the model given the questions that it has answered by looking at the difference between the predicted values and the ground truth values. And again, the ground truth values here are derived from the trained latent vector model, which I'll get into more specifically in a few slides. Anyway, so the task is given a budget n of the number of questions you want to answer, to choose a seed set of questions from all possible questions, which corresponds to all possible pairs of items. So you have n pairs of items that correspond to questions that minimize the expected loss of the binary classifier. So that's the loss, the difference between the predicted value and the true value. And in the paper, the authors extensively show and prove how this optimization task should be solved to optimally select these questions. All right. With that, I'll briefly explain the algorithm for selecting the actual questions. So it's an iterative, greedy procedure. And in each iteration, the task is to find a new question, to find a new pair of items. So your input here is the vectors of your questions chosen so far. That's the queue, the set of queue. So these are all the question embeddings. And a set of the vectors of all possible items. So given those two things, the output is a new question vector, which corresponds to the difference of two item vectors. So as a first step, the authors decompose the space into two components. U is the subspace of all vectors of questions that are already asked, so they're in your set of questions to ask. And another space that's orthogonal to it. And to illustrate this, there is this picture. So in this case, we choose only one question, E1, and all item vectors are decomposed into two components. One is orthogonal to E1 and one is parallel to it. And then the first step is to filter out a bunch of item vectors, namely all the points that have a large component parallel to U, because the subspace U represents the space of items about which we already asked the question, the user's preference. So that's kind of the known information. And to select a question, we need to find a vector with a large component from the subspace orthogonal to U and a small component from the subspace parallel to U, because that's the known information. And so the first task is to filter out all these points that have a large component parallel to U, I presume for efficiency reasons. Having done that, the next step is to project all the remaining points into the space that's orthogonal to U, so that represents the new information, the unknown information. And then the task is to take the two items with the largest distance. So then you have the ones with the largest component in the space orthogonal to U. Right. So if that's all clear, then we can move on to the experimental setup. So to study whether this method provides enough information to build a high-quality list of personalized recommendations for cold users or cold start users, the task is to measure the impact of the preference elicitation procedure used on the final quality of the recommendations. So we're going to evaluate the final recommendations using the preference elicitation method proposed. Then to do that, we have a few baselines. So as I understand, the authors are the first to propose a preference elicitation method that creates a static questionnaire containing relative questions. So we had, in prior work, there were dynamic questionnaires and or absolute questions, but not in this particular configuration. So there were no directly suitable baselines. So the authors took 3 baselines designed for solving similar but not identical tasks, namely the forward greedy baseline, that's a static method containing absolute questions as opposed to relative ones, which is most similar to the proposed method, well, except for the fact that it uses absolute questions. And it's also cast as an optimization problem, as is this paper's method. And then there's 2 other baselines, the bandits and pairwise decision trees, which both create dynamic questionnaires by asking relative questions. So that means that the questions are not independent from the user nor the questions. So that has some constraints on the implementation. And a random baseline. Right, then also there's 2 different experimental conditions for running these experiments. So one is called the real condition, where you take as a set of possible items, possible questions, only those items that a user has rated. But it brings 2 issues. One is that the optimal items may not be present. I mean, you're dealing with sparsity. And this also means that you'll have different questions for different users, as different users rate different subsets of items. So to kind of counter that, the authors also propose a simulated condition in which the underlying idea is to use your latent factor model to get predicted ratings, and use these predicted ratings to actually answer both the questionnaire questions and the test questions. Right, I did not mention, but for the idea is that for each user you take a subset of questions that you use for training, which are items that a user has rated, and a set of questions used. So the training questions are the candidate questions for your preference elicitation method. And then you use test items that you use for evaluation. Okay, then on to the numbers. So in this paper there's 2 research questions, and in these slides we focus on the second research question, which is what is the impact of the preference elicitation method used on the final quality of the recommendations, as I said before. So the idea is that you use the same latent factor model, but you use different methods to generate your questions. Now, on to the results. So there were 2 experiments, one with the movie lens dataset and one with Amazon Books dataset. We're looking at precision at 10, ranking metric, because the final goal is to provide users the most relevant recommendations. And what we see here in this graph is in red, we see the proposed method, SPQ. And what else do we see? And there's a top and bottom plot, and the top plot is the simulated experimental condition, and the bottom plot is the real experimental condition with the squiggly lines. And what we see here is that all methods provide the same performance for questionnaires with a length less than 5. So up to 5, it doesn't really matter. You may even go for random questions, it appears. And we also see that SPQ, the proposed method, works significantly better than other methods if the budget is larger than 20 questions. And finally, in the real condition with a medium-sized budget, SPQ significantly outperforms all other algorithms. Then on to the next data set. So similar patterns here overall. SPQ achieves near perfect performance where the set of questions is larger than 15. And for smaller budgets, SPQ has similar but statistically significantly better performance than bandits, which was noted by the authors. Then in summary, so we saw roughly with these 2 experiments that for small budgets, it doesn't really matter. For larger budgets, between 5 and 15, you want to go with anything but random, it seems like. And for longer questionnaires, SPQ is the best choice. So to summarize the summary, what have we done? So the authors approached a new user coldstart problem. They introduced a static relative preference questionnaire. They mapped their preference elicitation problem to an optimization problem, for which more details are in the paper, and I highly encourage everyone to read it. They theoretically solved it, and they provide better performance than the baseline. That is that. So if you have any questions, I'm afraid I won't be able to answer them. But you can send them to Anja, or let me know after, and I can forward them for you. The code is available on GitHub to rerun these experiments and to reproduce the results in the paper. There is also a reference of this paper in the slides. Please read it if you find it interesting. And then finally, the authors would like to thank all these organizations. Thank you.
Thank you very much.